Hello, everyone, and thank you for joining us today. Welcome to Megger's Testing Tactics webinar series. Today's topic is on-site installation analysis for GIS using UHF and Acoustic PD measurements. My name is Michael Fleischer, and I'm the Digital Marketing Specialist for Megger. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. There we go. You can submit questions at any time during the presentation by typing in the box highlighted in red, and it will read the questions out during the Q&A segment at the end of the webinar. Additionally, a certificate of attendance, copy of the presentation, and link to the recording of this webinar will be sent to all attendees in 2 business days. Our presenter today is Charles Nybeck, Applications Engineer. To assist with our question and answer session, we will also have joining us Matthias Wiesmann, Project Manager. All right, let's go ahead and get started. Thank you for joining us today, Charles.
Absolutely. Thank you, Michael. Appreciate the introduction. And hello, everybody. Welcome for joining us. My name is Charles Nybeck, and I'm an applications engineer here at Megger. And as Michael said, today we will be discussing on-site installation analysis for GIS using ultra-high frequency, or UHF, and acoustic partial discharge measurements. All right, for today's agenda, we'll start by discussing an introduction to GIS partial discharge testing. And then we'll move on to the sensors used for partial discharge measurements on GIS, followed by on-site ultra-high frequency, or UHF, partial discharge measurements. Then we'll move to look at a couple of examples of UHF phase resolved partial discharge patterns, where we will discuss what a phase resolved partial discharge pattern is as well. And then lastly, we will look at on-site acoustic partial discharge measurements on GIS systems. Let's get started by covering the introduction to GIS partial discharge testing. So gas insulated switchgear is compact, reliable, state-of-the-art technology that incorporates gas, which is typically sulfur hexafluoride, or SF6, at higher than ambient at pressure as an insulated medium. So if we look down here, we have a picture of a GIS system, and here we have kind of a diagram or cross-section of a GIS, where here we have our shell or outer enclosure. We have an insulating barrier and our high voltage conductor. And then this gray area is our insulating material, which is our SF6 gas. Now, the gas is pressurized to increase the dielectric strength according to Paschen's law, which relates the breakdown voltage between two electrodes. In this case, could be the ground potential and the high voltage potential, to pressure and the gap distance. And since this case, the distance between the two is fixed, if you increase the pressure, you increase the overall breakdown voltage, therefore increasing the dielectric properties. Now, switchgear are very complex systems that often include things such as circuit breakers, switches, bushings, buses, CTs, PTs, metering, controls, relays, and so on, which means that when there is a failure, this can lead to long outages, which can last days or months to acquire those replacements and then make the repairs. And this can also lead to very high repair costs as well. But if we did partial discharge measurements, we can prevent these failures by early detection of defects prior to the fault or failure that requires you to have that expensive outage. Now, there's several different defects that can happen within a GIS system, such as the free particle. There's also floating potentials on your high voltage conductor here, an impurity with your insulator. There could be a gap within your insulating barrier and your high voltage, or even a metal protrusion on your high voltage conductor. But one thing that's in common with all these is these all affect the electrical field within the GIS. And to look at that, we'll take an example of the metal protrusion, where here we have a simplified cross-section of a GIS, where again, the enclosure is at our ground potential. The insulating material here is our SF6 gas, and then we have our high voltage conductor. Looking at the simplified cross-section, the design for this in terms of the electrical field is supposed to be uniform throughout the GIS. So we can see a nice uniform electric field or homogeneous electric field throughout the GIS system. Now, this electrical field is also designed to be below the critical field strength in normal operation. And what that means is during normal operation, you won't have any arcing or sparking or anything of that nature due to the design of the electrical field being below that critical field strength. Now, if you do introduce something such as a metal protrusion on your high voltage conductor, that could change. So we see here that we have our protrusion on our high voltage conductor, and this creates an inhomogeneous or a non-uniform distribution of our electric field, where typically these were going out this way, and now you can see that they are now conforming around this metal protrusion. And that's typically due to the sharp edges in high voltage actually create field enhancements that allow the electrical field to kind of congregate towards that. So that can create a situation in which the field strength is actually above the critical strength. And with this condition, especially with the SF6 being an electronegative gas, which we'll discuss a little later, creates the conditions for partial discharge inception. Now, partial discharge does emit energy in several different ways. One of those is electromagnetic emissions in the form of radio waves, light, heat, and even very high frequency or ultra high frequency, which we'll look at later as well. There's also acoustic emissions, where the partial discharge that takes place actually creates a pressure wave that then creates a sound wave that propagates through the GIS system. And there's a slide to illustrate that a little bit later as well. And these are in the audible and ultrasonic ranges, so slightly lower frequencies than the electromagnetic emissions. And then also we have the chemical byproducts. So partial discharge is known to produce ozone, and ozone is a very corrosive byproduct. And particularly, and this is a problem in GIS because there's separate gas chambers that are isolated, and if you have a partial discharge event that creates ozone, which is corrosive, it could lead to damage within that gas chamber there. So ultimately, each one of these or all the discharges here lead to deterioration within your GIS system or your insulation system. Now, partial discharge testing, though, can indicate an imperfection or a defect within the system. So not only can you identify that there is a imperfection or defect through PD testing, but actually through acoustic emissions, you can localize it. So you can actually determine where in the system or where in your GIS system you're having or that partial discharge is taking place. And we'll look at an example of that at the last chapter of this presentation. Also, on top of identifying and localizing, you could actually classify the type of defect. And this is done by using the phase resolved partial discharge pattern that was mentioned previously. And we'll look at that, but through the measurement and the phase resolved partial discharge pattern that's received, you can determine what type of defect may be taking place within your system. So this partial discharge testing allows for the detection of risks and hazards, allows you to schedule the maintenance works around what's critical and what's not, and allows for ultimately the increase in reliability of your system. Here we kind of have a visual of the emitted energies by partial discharge, where we have our high voltage electrode, our ground electrode, and our insulation, where we have what looks like a void discharge and a surface discharge. And energy is emitted optically, so we can see here. It's emitted by pressure wave, by sound, so we kind of talked about that one previously. Electrically through discharge effects, dielectric loss, and high frequency waves, which is important. We'll look at that one. Chemical effects and heat. So when we talk about GIS specifically, we're looking more at the acoustic and the UHF measurements for on-site measurements. Now, the IEC 6270 covers the conventional measurement, which uses a coupling capacitor to decouple the partial discharge in an apparent charge measurement. but that's more of a factory measurement. We'll discuss that a little bit, but not so much in depth because the on-site measurement is going to include your acoustic and UHF measurements. Now, but just to kind of briefly discuss the conventional PD measurement, it is in accordance to the IEC 6270 standard that I mentioned previously, and it does utilize a coupling capacitor to decouple the discharge that's taking place within a high voltage asset. And therefore you can measure that discharge in, or a relative discharge in picocoulombs. One issue is when testing on site though with GIS is the customer expectation is about 5 picocoulombs, where the background noise is anywhere from 10 to 100 picocoulombs. And the background noise is the noise radiated by other high voltage assets or other high frequency assets that actually can impede your measurement. So kind of, for instance, the background noise, if it was 20 picocoulombs, you wouldn't be able to measure anything under that unless you were able to eliminate that noise through noise reduction techniques. Also, the IEC 6270 method is lagging in fault location because it just utilizes the coupling capacitor method, and it can't be applied in surface with GIS because we don't have access to the high voltage conductor to decouple the PD measurement through the coupling capacitor. There's also the chemical measurements. This is a slow process, so if you have PD taking place within an isolated section of your GIS, you may not measure it for some time, and this can, as we talked about earlier with the corrosive properties of ozone, this could lead to damage within the GIS. And also the barrier insulators that are in the GIS that separate the gas compartments limit the range of detection. Finally, you also have the optical method here, but certain defects can't be detected, such as void defects. Since they're in the middle of the insulation, it's going to be difficult, or you can't detect them via the optical method. Here we have an example of partial discharge within SF6 gas. So as I mentioned previously, SF6 is an electronegative gas. And essentially that means that it's more ready or more easily accepts readily available electrons, and a free electron is necessary for partial discharge to take place. So this leads to a very fast rise time in SF6 for the discharge, and that's in the area of 100 picoseconds. And this translates to a frequency spectrum of up to several gigahertz. So we can see here the fast rise time of the discharge current within SF6. And just to kind of give you a comparison with nitrogen, which is representative of air insulation, since air is 98% nitrogen, the rise time is more in the area of 1 nanosecond, which translates to a frequency spectrum of 100 megahertz. So you can see the large difference there and the rise time and therefore the frequency, which makes us have to take these certain measures and use certain sensors or antennas to decouple and measure these partial discharges. Also, as we had previously mentioned, the GIS or gas insulated switchgear is a very complex system and has complex geometry, as you can see with the diagram to the right. And this leads to high frequency effects such as reflections and signal attenuation. Also, the impedance of the waveguide, which is the GIS enclosure itself, as the PD takes place, the enclosure actually acts as a waveguide, but this is a function of the differing diameters within the GIS system as well. Also, even things such as surface roughness can influence the signal propagation through high frequency effects such as dispersion. All of these effects, as I mentioned, are highly frequency dependent. And if we look over here to the discharge, we can see a nice clean rise time and relatively clean settle time here. But this is at the point of the discharge. Now, by the time you measure it, that PD pulse is actually converted to a pulse package. And due to those high frequency effects, it looks more of something of this nature by the time you measure it, due to the reflections, attenuation, and dispersion. There are methods to kind of clean this up, and we'll talk about that, such as a frequency converter unit that creates a package envelope um, that allows you to analyze this a little more easily, and we'll discuss that later. So as we mentioned, one method for detection of partial discharge within GIS is using ultra-high frequency or UHF methods, in which the partial discharge causes electromagnetic waves that propagate through the GIS structure, as you can kind of see here with the illustration, where again, the GIS structure itself acts as a waveguide. These signals are very fast, so approximately 2/3 the speed of light, which just for reference is 300 million meters per second. So 200 million meters per second for the signal, so very fast signals. These frequencies are several 100 megahertz to some gigahertz, as we talked about, but the range is limited due to the attenuation and reflection effects that we talked about, as well as GIS not being a very good wave conductor due to the skin effect. And the skin effect is the fact that the signals travel on the outer area of a conductor rather than the center, and this is especially with high frequency measurements or high frequency signals as well. Also, the epoxy barriers as seen here, these insulators attenuate the signal as they try to pass through. There are several different sensors and antennas used to detect different sensors or different signals when we'll look at those. But ultimately, when you're doing UHF measurements, the UHF signal must be able to exit the GIS. And this can be done internally with embedded sensors. It can be done through Windows sensors or through epoxy barriers with external flange sensors. Another method for partial discharge detection in GIS is acoustic measurements, where again, like I said, the partial discharge actually causes a pressure wave that creates, or that a sound wave, and that propagates through the gas and the metallic structure. Now, these signals are much slower. We can see anywhere in the range of 130 meters per second for the SF6, up to 6,300 meters per second for the aluminum. Therefore, these frequency ranges translate more to the kilohertz and megahertz range, but these still are affected by dispersion and attenuation that limit the detection range. Now, one advantage is that you get really good sensitivity if the sensor is close to the PD source, and that therefore that's why the acoustic method is often used for PD localization, and we'll take a look at an example of that. So now that we've covered the introduction to partial discharge testing in GIS, let's go ahead and take a look at the different sensors used for measurements on GIS. Starting with the external flange sensor. So the external flange sensor uses the unshielded spacers of the flanges that connect the isolated gas compartments. And this allows for retrofitting without opening the GIS. So if you have the epoxy insulator here, this allows for the exit of the UHF signal. Because the rest of the GIS, as we know, is metallic and won't let the UHF signals escape. So if you have the ability to, or if you have the availability of an epoxy insulator on the flanges, you can use these external flange sensors. And we have some examples here where you can see this is a permanent installation with this copper belt around the external flange, and the external flange sensor here in this red box. And another example here of a temporary installation where you have the external flange sensor with our frequency converter unit that I was talking about, that you can use to create that envelope for your partial discharge measurement. So it converts the high frequency measurement down to a lower frequency in the area of 1 megahertz for the acquisition system. And over here we just have the impulse generator. So it looks like they're kind of doing an on-site sensitivity check, which we'll discuss a little later. Ultimately, these do have a little bit lower sensitivity since you're decoupling the UHF signal externally to the GIS. Alternatively, there are window sensors. So these can be used in the inspection windows of GIS, in which it is required that the window diameter be larger than 60 millimeters. And this is due to the wavelength and therefore the necessary diameter of the window for the UHF signal to escape. This also allows for the retrofitting without opening any GIS with the availability of the inspection windows. So here we can see we have our window sensor attached to the inspection window. We have our frequency converter unit, and then the coaxial cable, or just RG58, going out to our measurement instrument. So you can see the several different window sensors, and then our frequency converter unit used again to lower the frequency, or to shift the frequency to lower frequencies. Then finally, for UHF sensors, there's the integrated or embedded UHF sensors. These have a frequency range of about 200 megahertz to 2 gigahertz and offer the best signal to noise ratio due to the fact that they are internally decoupling the UHF signal. So they're going to be embedded into the GIS system and allow for direct decoupling of the UHF signal as it propagates through the GIS. These are typically installed during the manufacturing process and are often provided by the GIS manufacturer. Alternatively, though, there is implementation by third-party embedded sensors, but this requires close cooperation with the GIS manufacturer. And another thing, you can see the embedded sensor here and implementation of it in this image here. But one thing, if we look, we not only have the frequency converter unit, but we also have an input protection unit. And this is due to the fact that since the sensor is embedded into this gas insulated switchgear, and due to the inherent properties of switching, we want to protect it from any transients that may damage the unit. Here is a diagram of connections for the UHF testing using window sensors or embedded sensors. So you can see that you can have any window sensors or embedded field probes. And if you have an embedded field probe, you can see through this image that you include, like we said before, the protection unit, and then you have your frequency converter unit, and then simply your RG58 cable out to your measurement instrument. If you have a window sensor, no need for the input protection unit because it's an external sensor. So you just use your frequency converter unit and then again out to your measurement device, and you're ready to perform your measurement. Looking at the external flange sensors, we can see this is an example of an external flange that's shielded, but it has this nameplate cover here, which is sometimes typical in some of these flanges. And if you remove this, you can see the epoxy insulator that's filled that area. And we can utilize this to have the UHF signal escape from the GIS system. So you can see that with that removed, we can take the external flange sensor, place it around the flange. We have our frequency converter unit, and then again back down to the measurement system and ready to perform the measurement. Same thing over here. I guess this one's slightly difficult to see, but this gray box on here on this permanent installation is our external flange sensor. There's a frequency converter unit here, and then down here is a pulse generator. So again, it looks like they're performing a sensitivity check on site before their measurement. But like I said, relatively straightforward. You just need to find a place where you have no shielding on your external flange, place your sensor, your frequency converter unit, and back to your measurement device. So aside from UHF measurements, there are also acoustic measurements. And again, as I mentioned before, these are typical for localization. So there's different acoustic sensors, so 75 kilohertz or 150 kilohertz as well, depending on the application. And you can see different ways that they're used as well, in the sense that you have this kind of toe strap with this fixture, this SFX1, that holds the acoustic sensor to the metallic structure of the GIS. Alternatively, though, there are these magnetic fixtures that can be placed anywhere on the GIS structure as well. Another thing is you'll see this preamplifier that's typically used with the acoustic sensors. They're optional, but they offer amplification of the signal measured to be transmitted to the actual measurement device itself. And here's an example. Here we have an example of the SFX1 strapped around our GIS structure. We have our acoustic sensor here in white, and then our preamplifier, and out to our measurement device. So again, relatively straightforward. It's just your acoustic sensor, your fixture, the preamplifier, and then out to your measurement device, and you're ready to perform your acoustic measurements. So now that we've discussed the sensors, let's go ahead and move on to discussing on-site UHF PD measurements. When performing on-site UHF PD measurements, it's important to ask questions before testing to get as much information as possible. So these questions can involve the reason for testing. Is it maintenance? Was there a fault? Get some idea as to why you're out there testing. It can be the size of the GIS and voltage level that's important to know. Drawings and schematics, so you know what sensor, if they have embedded sensors readily available, where they are, the different gas compartments, and so on. Previous measurement data is always nice to know, so that way you can do some trending or at least some comparison. The types of embedded sensors they have and the connector types, so you want to know what you have available before you get out to the field to take the measurement. Also, do they have any unshielded flanges available that we've talked about? So here we have an example of one here on out in the field where the external flange sensor is placed right here. You can see with the frequency converter unit and out to the measurement device. If there aren't any external flanges available, are there any windows available? And what are the size of the windows? So you need to know the diameter, pitch, circle, and screw size, so that way you can apply that window sensor to the observation window. And it's always nice to know the age of components as well to get an overall understanding. So once you actually get to perform the on-site measurement, one of the first things you want to do is check for a synchronization signal or a power signal. So that allows you to, when you perform your measurement, to overlay the measurement or compare it to the operation voltage of the system. And this gives you some indication of the type of defect when you're looking at the phase resolved partial discharge pattern that we'll look at a little bit later. Next, you want to check to see if your UHF sensors are applicable, which ones you have that are applicable. So do you have any embedded sensors? Do you have window sensors? Do you have external flanges that are non-shielded where you can use the external flange sensors? Now, if you have embedded sensors, it's recommended to use the input protection unit. That way, due to the inherent switching of the switchgear, you don't damage anything. And then, of course, the frequency converter unit to convert that high frequency measurement down to a lower frequency for transmission to the instrument device. This allows for the signal cable to be up to 50 meters and just using simple coaxial cable or RG58. Now, if you don't have embedded sensors, you can check for window sensors to apply your window sensors, again, given the fact that the diameter is greater than 60 millimeters. You want to, and this, again, you want to ask this before going out on site, so that way you're prepared with the appropriately sized window sensors and hardware to attach it. Now, with the window sensors, you don't need the input protection unit as said. You just attach or apply your window sensor to the observation window. You have your frequency converter unit, and again, your RG58 up to 50 meters long going out to your measurement instrument. Then finally, if you don't have either of those, the embedded or window sensors, check for unshielded flanges. So here we have an example of a GIS from ABB where, again, we saw this previously where this flange is shielded, but it has this kind of nameplate covering. And we can remove this to reveal the epoxy insulation underneath. Now, then we can use the external flange sensor, place it right over that. And then again, as we saw before, our frequency converter unit, again, no input protection unit necessary for this since the measurement is external, and then out to your measurement device, and it allows you to perform your measurement by the UHF escaping through those epoxy or casting holes, as you see here as well. Then, once you figure that out, the next thing to do is to perform an on-site sensitivity check, in which you inject a UHF signal using a generator. So it can be a calibrator, generator calibrator, into a UHF sensor. So that could be embedded, an external flange sensor, or a window sensor, and compare to the signal to the surrounding sensors. So you always want to start with the highest value and then check for a clear impulse on the phase resolved partial discharge pattern in a scope display. And what I mean by that is, if we look at the image on the right here, we can see that we have our impulse generator down here attached to an external flange sensor. So we can see the external flange sensor installed here. We have our impulse generator, so it's kind of, the image has been blown up here. Now you inject that impulse and measure on the surrounding sensors, which we have one on this flange here, so the external flange sensor, and you can see with the difference between the generator off and the generator on. And you just want to verify that the UHF impulse signal can be detected at least by the closest sensor, but ideally, other sensors as well. So again, showing the benefits of performing that on-site sensitivity check. All right, now let's go ahead and take or look at a couple of examples of UHF phase resolve partial discharge patterns. So first, before we go into the examples, kind of want to discuss, the evolution of the representation of partial discharge, where first we had the early style meters that you can see are analog dials and analog metering. Next was the oscilloscope and the Lissajous view. So these were quite an advance, where you actually get to look at the partial discharge in relative to the phase. So two different ways of looking at that. Next, there was the count distribution, where our y-axis is the number of discharges, and our x-axis here is the discharge in nanocoulombs. Finally, or not finally, but next there's the VQN, which is our PRPD pattern. And believe it or not, due to even though this is a two-dimensional plot, it's a three-dimensional graph. What I mean by that is, our x-axis is our phase angle. So you can see the synchronized voltage that we had talked about, that's important to double check. And then you have your magnitude of discharge in your y-axis. Now the third dimension of this graph is actually the color. So the number of discharges is represented by the color, where the yellow is the highest number and this gray is the lowest number. And also, you have three-dimensional patterns, but I kind of wanted to take an example, or take a moment to look at the two, because if you actually look at these two patterns, it's the exact same measurement, just one is displayed in a three-dimensional view and the other the two-dimensional view. And one advantage of phase resolve partial discharge patterns is, as we talked about, is the recognition of the type of defect. If we look at this phase resolve partial discharge pattern, you can actually see we have what looks to be a void discharge by this part of the pattern here, and maybe even another, what looks to be maybe a second void. But then we have this other triangle that's on both sides here. And this indicates, or looks to indicate, surface discharges. So now you have two different types of defects as well. And this, if you look at this three-dimensional plot, it's a little bit more difficult to determine that. So I prefer personally to use the phase resolve partial discharge patterns here. So looking at a couple of examples, first we have the moving particle, or the hopping particle, within a GIS, and this sometimes happens during installation if there's some metallic particles that fall into the GIS. So they enter the GIS again during assembly, and what happens is, when you apply your voltage, they can be lifted by the electrostatic forces and jump towards the high voltage conductor, and if they get close enough, that can actually cause a breakdown. And this is indicated, you can see, by the phase resolve discharge pattern, where we have these two humps here, these two bumps through the different positive and negative applied voltage at their peaks. Here we have another one where they're just kind of a lower magnitude of discharge, but again, you can see clearly the hopping particle pattern. Next is a protrusion. This is mostly due to scratches due to the care during assembly. And these are often low PD levels, low discharge levels, but the sharper the tip, the easier it is to detect, because as we mentioned near the beginning of the presentation, that these sharp points can actually cause field enhancements and kind of cause a localization of that electrical field, so they can cause higher discharges. And the shape of the tip can change over time. So again, you can kind of see the indicative pattern of the protrusion discharge, again, kind of being not quite the humps we saw before, but being these tall kind of column discharges at the positive and negative applied voltage. And then here we have an example of void discharges where the partial discharge inception requires that starting electron that I had mentioned earlier, which makes the void discharges difficult to detect during acceptance testing, as you may not have that electron readily available. So GIS manufacturers have implemented PD testing using X-rays to excite that and have that electron, have that available electron to try to identify voids. Here you can see the void. We saw them kind of earlier, but you can see this arc here, and another one here where we have voids, and you can see the high number of discharges as well as the high magnitude. But as well, not only can we see we have one discharge, but if we look down in this case, as this is a little bit more clear than the previous one that we looked at, but we can see that we have 1, 2, 3, 4, maybe 5 voids within that insulation. So again, the phase resolved partial discharge pattern has a lot of benefits in determining not only the severity but also classifying the type of defect that you have. Now the phase or the measurements for GIS are typically, or at least the on-site measurements, are non-conventional partial discharge measurements. The sensitivity verification is performed to kind of replace the calibration, and it's a two-step procedure that's covered in the C-grade documents listed here, where essentially for unconventional UHF method, a calibration to a parent charge or that picocoulomb value is not possible. Instead, the measurement is in decibel microvolt or decibel milliwatt. As you can see here, also, if you have your partial discharge taking place, you have a certain magnitude here of discharge, and as you propagate through, you have this lower magnitude. So to actually calibrate, you would need to have that this discharge in several different places to actually have a calibration for each UHF sensor. So that calibration is not really possible. So instead, there's a sensitivity check performed, and that sensitivity check is first in accordance to the IEC 62 method, where you use the coupling capacitor and you insert a artificial defect, and this is kind of in the factory environment, of 5 picocoulombs, and then you have then you inject a signal or an impulse into that same sensor and try to determine what that impulse is that equals the 5 picocoulombs. So it's not a proportional charge value, but then you go out to the field and perform your second part of the sensitivity check, where you inject that known impulse into the neighboring sensors to make sure that you can see that impulse over your noise floor out into the field. And you compare that the signal amplitude to your different sensors within the GIS. And to ensure that you get a view of the impulse, you can adjust your gain through your measurement device, and it should be about 50 to 90% of your full input view. So now that we've discussed the examples of UHF measurements, or the partial discharge, phase resolved partial discharge, let's take a look at on-site acoustic partial discharge measurements for GIS. Here we have an example where there are no embedded UHF sensors or no openings in the GIS shielding for external flange sensors. So therefore, acoustic sensors are used to detect the sound waves that are a result of the partial discharge taking place. And this test set is comprised of acoustic sensors, the preamplifiers we discussed previously, a PD measurement system, in this case the ICM system here, and then an external oscilloscope for just kind of redundancy and measurement and comparison. So initially, there's a single acoustic sensor that's placed at the gas chamber holding the bus bar disconnect. So we can see, again, our GIS gas chamber here, our enclosure, and here we have our bus bar disconnect. And we place the sensor here where the X direction is going along. Now, there's no voltage sync, as we can see here. So there's no conclusion as to what the type of defect is, whether it's on the high voltage or on the ground side of things. And also, if you look, there's only a percentage on your y-axis since there's no calibration possible with the acoustic measurement either. But if we look at this phase result partial discharge pattern, we can ultimately see that there is indeed some discharges that are taking place. So it does warrant further investigation. So now what happens is we placed 4 acoustic sensors closely together in the X direction on the GIS enclosure itself and taking the measurement. So here we can see the diagram where we have sensor 1, 2, 3, and 4 placed in the X direction on the shell of or on the enclosure of the GIS. Looking at the actual measurements, we can see that the sensor 4 actually received the acoustic measurement first. So we have 4, 3, 2, 1 in that order as to what the acoustic measurement or the acoustic signal reached. So we can determine that the PD signal or the PD defect must be downstream in the X direction as it reached sensor 4 first. So the next step is to just simply move the sensors along the enclosure of the GIS. In this case, again, just taking them in the same order and moving them along the X direction. Looking at the measurement now, we can see that the third sensor actually takes the measurement as soon as they are right on top of the reference. The sensors 2 and 4 are equal distance from 3, and you can see that the PD reaches them, or this acoustic signal reaches them at about the same time, which makes sense. If the PD defect is at 3, then the signal would reach 4 and 2 at the same time if they're equal distance apart on opposite sides. And then obviously 1 would have the signal last. So we know that the PD source must be located at sensor 3. Looking at kind of this closer so everybody can see it, again, we have sensor 3 here, and you can see that sensor 3 is right on top of your reference, or right on top of your measurement, and you can see the delay on channel 3 is 0 microseconds. So we know the PD defect is there. Again, between 4 and 2, the difference is only less than 3 microseconds. And then you can see the lag behind channel 1 since it's further away from the defect. Then there was the phase result partial discharge measurement was made. So we can look at the PRPD patterns here. And we know that 3 is where the partial discharge is taking place. So if we look at sensor 3's phase result partial discharge pattern, you could actually see quite a little bit more discharges taking place in comparison with the other patterns where it's not quite as prevalent. So we again just kind of a more of a confirmation that the PD is in right at where sensor 3 is. So now that we know the location or the PD source is at the location of sensor 3, with the previous configuration, the next step is to take the 4 sensors and place them around the circumference of the GIS enclosure to determine if the PD is on the high voltage or the ground or where it is at in the GIS at that location. So then when we perform the measurement, we can actually see, this is by the Tektronix oscilloscope view you see here, that signal 2, or sensor 2 rather, received the acoustic signal first. So this gives us an indication that not only is the PD here in the X direction, but if we look at the cross-sectional view, the partial discharge defect is here at the sensor 2. This can also be verified from the partial discharge measurement system. So this was the oscilloscope, and now we have the partial discharge measurement system where, again, channel 2 or sensor 2 is right on is the first one to receive that partial discharge signal. Now there's 1 and 3 that's on either side, but due to a seam, 3 was placed a little bit further away than 2, but you can still see that they're only differ by 25 microseconds in travel time between the acoustic signals. And then of course 4, being the furthest away from the PD signal, is the last to reach. So now we've not only identified that there was a problem within the GIS, we located where it was in the X direction, and now we've even identified that it's at the base or the ground potential of the GIS. So just kind of shows the ability for the acoustic measurements to localize PD defects within GIS. Here we have the phase resolved partial discharge patterns. but since they're all placed in the circumference around the defect itself, right on top of the defect, you can see that they're pretty much identical throughout, but shows us that we do have a strong pattern when the sensors are placed in that location. All right, so in conclusion, the PD occurs due to imperfections or defects that cause deterioration, emitting energy in several different ways, where primarily we measure through UHF or acoustic emissions. Now, PD and SF6 emits UHF and acoustic signals, which are wave-guided by the actual GIS enclosure, but are susceptible to complex propagation and susceptible to high-frequency effects such as dispersion, reflections, and the differing and attenuation. The UHF PD pulse package can be picked up by various different sensors. So this can be, as we talked about, this can be our window sensors, our external flange sensors, or if available, the embedded sensors that offer the best signal to noise ratio. And UHF and acoustic measurements are not measured in picocoulomb and therefore cannot be calibrated. But the UHF can be used for acceptance testing by your sensitivity verification that we kind of briefly covered in this presentation. And finally, acoustic measurements can be utilized if there are no options for UHF measurements, or even if you have a UHF measurement and have determined that there's a defect, and you can use them not only to determine also if there's a defect, but primarily for localization, as we saw in the last example where we were able to determine where in that GIS system the PD defect was located. All right, thank you very much. And that's all I had for today.
Right. Good deal. Thanks, Charles. So it looks like at this time the presentation portion of the webinar is concluded. So we'll take some time to answer as many of your questions as we can. If you have any questions, please submit them now into the Q&A box on the GoToWebinar control panel. For those of you that are leaving, when you close the webinar window, a survey should pop up on your screen. We would greatly appreciate it if you could take a couple of minutes to provide your feedback so we can continue to improve upon our future webinars. On that survey, there's a field where you can also request a demo or a quote on any Megger products. A copy of this presentation, certificate of attendance, and a link to the video recording of this webinar will be emailed to everyone in about 2 business days. You can also view video recordings of previous webinars, as well as register for our upcoming webinars on our website at us.megger.com/webinars. All right, well, let's jump into your questions. The first one I have, I'm going to be directing to Mateus. Are PRPDs recorded with UHF comparable to the IEC 60270 measurements?
Okay, thank you for that question. They are, but not entirely. So we have to look out for slight differences in there. If I record a PRPD in UHF or according to IEC 60270, doesn't make a difference on when I look at it first, because the form and the shape of the measurement that I'm seeing in the PRPD basically looks pretty much identical. However, there are some important differences that have to be considered, and that is especially the measurement on the y-axis of my graph. So while the IEC 60270 measurement gives me values in picocoulomb, as Charles has explained in his webinar, in picocoulomb we can't measure when we are applying the UHF method. So if we are measuring in the UHF method, we are measuring a voltage, and accordingly there's a slight difference in the value of the amplitudes that is been displayed in my PRPDs, but otherwise they are comparable, yes.
All right, awesome. While I have you, I have another question that I can send your way. What options are available to eliminate noise signals?
Various different options. So the most desirable solution for noise signals is usually to get rid of the source itself. But obviously, unfortunately, that is typically not the case. So we have to take a look at what type of noise we are facing and what would be the best approach to eliminate it. In a lot of cases, I have the option to adjust the frequency range in which I'm measuring. And if I have noise that is prominent in a specific range of frequencies, then I can simply measure at a different frequency, because my PD signal is usually a quite broadband signal. So accordingly, I pick a signal where I can measure my PD but not my noise. An alternative solution would be to utilize the gating functionality that is available with most instruments. For gating, I pick up the noise signal with an external sensor that can be a disturbance antenna that picks up airborne signals, or a CT, a HF CT that picks up noise that might be reaching our measurement through the grounding of our setup. And then I provide this noise signal to my instrument, the gating input of my instrument, and it blinds out the noise signals from my measurement. So there are different options available, and it depends a bit on the type of noise that we are facing.
All right, thanks a lot. I'm sending this one back over to Charles. Charles, when would it make sense to install permanent monitoring?
Sure, that's a great question. So permanent monitoring obviously has its benefits. So things that you want to kind of ask is the criticality of the asset that's in question. So and the budget that's in place. So obviously these permanent monitoring solutions are going to be slightly more expensive than you know your permanent or your periodic portable instruments and portable measurements. But they also offer a lot of benefits. So if you have a critical asset, or if you have performed measurements on an asset and you determine that there is a defect and you kind of want to keep a closer eye on it, you can install these permanent monitoring solutions that allow you to monitor 24/7 the partial discharges. You can always look at the previous recordings and phase resolve partial discharge patterns, and also allows you to set alarm levels to where if you get a discharge above a certain threshold, it will set off an alarm and can alert you. That way you can take a look at what's happening, and you can even do this remotely. So there's a lot of benefits there, but it really determines on the criticality of that asset and the history of that asset, of course. So if there's known issues in that asset, it may be nice to monitor it so that way you don't come up with an unexpected fault or failure that causes you to have an outage.
Thanks, Charles. Back over to Matthias. Can the acoustic measurements be calibrated?
Nope. The acoustic measurement as well as the UHF measurement are the non-conventional PD measurement methods, and for those we have the amplitude that our measurement system picks up does not only depend on the value of the discharge itself, but also how long the signal has traveled through which geometry and signal path, and therefore no, it cannot be calibrated in picocoulomb.
All right, thanks a lot. Back over to Charles. Is there a continuous PD monitoring system, and what kinds of sensors and solutions are used?
Sure, absolutely. So there's continuous PD monitoring systems for really essentially any high voltage asset, well, or components as well. But and specific for gas insulated switchgear, there you saw a couple of examples actually in the presentation where instead of the blue belt where that had that external flange sensor on it, you could utilize the copper belt that is there fixed for permanent installation. So there you could still use these same sensors. So the sensors are still going to be pretty much the same as far as external flange sensors. You could use maybe CTs as well, but and you could utilize these for permanent installation and monitoring of your GIS system.
All right, back over to Matthias. For embedded sensors, how many sensors are expected to be on a typical GIS breaker bay or on a bus section?
That's a really tricky question because it depends on a lot of different factors. The way the electromagnetic wave travels through the GIS is depending on the geometry of the GIS. And it even comes down to the roughness of the painting, how the exact signal transmission within the GIS is actually happening. And accordingly, you have a different attenuation profile for each type of GIS. It depends on the voltage level, but there are also differences between different manufacturers. And then you have to take into consideration that different type of sensors have a different sensitivity. So some of them are better than others. And accordingly, it depends on so many factors that you can't give a precise answer to that question. However, what you can take into consideration is that a typical setup would be, for example, to have one UHF sensor on both sides of your circuit breaker, and then further sensors depending on the length of the GIB ducts that are connected to the GIS. So if you have a short cable exit right next to the GIS, then 2 to 3 sensors could be sufficient. If you have long GIB ducts, then you can have multiple additional sensors along these GIB tubes. So it's unfortunately something that can't be answered that clearly.
All right. It looks like we have time for one more question today, and we'll keep it here with you, Matthias. Is it good to make acoustic measurements first, followed by UHF sensor measurements? And how do you physically locate the location of PD to start with?
The typical approach is that you start with an electrical measurement. The reason for that is that the electrical measurement is more reliable than the acoustic measurement because it is less easily disturbed. And accordingly, performing an electrical measurement will give you the indication if you have a PD source within your GIS. And only if the electrical measurement tells you there is something, then you apply the acoustic measurement to pinpoint down where it actually is within your GIS. With the electrical method, you do have, with really sophisticated equipment, the option to go for a time of flight measurement, but the electrical signals are way quicker. So you will get a less detailed and precise location of your measurement. The acoustic signals are slower, and accordingly, it's easier to identify the location of PD. So first, electrical for identifying if there is PD, and then acoustic for identifying where that source of your signal is located.
All right, thanks a lot. It looks like that's all the time we have for our Q&A session today. We apologize if we didn't get to your question, but we will be working to follow up with you offline. As a reminder, a copy of this presentation, certificate of attendance, and a link to the video recording of the webinar will be emailed to everyone in about 2 business days. I'd like to thank you all for attending. If you could, please remember to answer our survey. That survey will also include a field for you to request a quote or a demo if you're interested. But once again, I'd like to thank you all so much for attending, and I hope you all have a great weekend.